My name is Ritvik and I'm from the branch Data Science Section B. Today I'm going to give a presentation on the topic Convergence and Distribution, subject probability and statistics. Let's go to the next slide. Firstly, we have to know what is convergence and distribution. Convergence and distribution is a concept and probability theory that describes the behavior of a sequence of random variables. It states that as the number of variables in the sequence increases, the probability distribution of these variables tend to converge to a specific distribution function. This convergence is not about the variables themselves, but rather about the distribution they flow. It is denoted as xn to dx and implies that for any value x, where the distribution function is continuous, the cumulative distribution function of xn converges to the cumulative distribution function of x as n approaches infinity. Let's go to the next slide. Let's see how convergence and distribution is helpful in probability and statistics. Convergence and distribution is of great importance in probability theory and statistics as it allows us to make inferences about the behavior of random variables. It provides a framework for studying the limiting behavior of sequences of random variables. Even when exact distributions are unknown, convergence and distribution enables us to establish key results such as the central limit theorem, which underpins many statistical techniques. It also allows us to access the adequacy of approximations and model assumptions by understanding how random variables converge in distribution. We can draw meaningful conclusions and make statistical inferences based on large samples or asymptotic behavior. So this is how convergence and distribution is helpful in probability and statistics. Let's go to the next slide. In this slide, we are going to learn the modes of convergence. Modes of convergence in probability theory and statistics refer to different ways in which a sequence of random variables or functions can approach a limit. The three main modes of convergence are pointwise convergence, almost sure convergence, and convergence in probability. Pointwise convergence focuses on the behavior of random variables at specific points. Almost sure convergence ensures that random variables converge to a limit with probability 1. Convergence in probability emphasizes that the probability of a random variable deviating from its limit approaches zero as sample size increases. These modes of convergence provide different insights into the convergence properties of random variables and have various applications in theoretical analysis and statistical inferences. So, I hope that you have understood these are the modes of convergence. Let's go to the next slide. Then we have to learn about the topics central limit theorem. Let's take a look at this. Central limit theorem (CLT) is a fundamental concept in probability theory and statistics. It states that the sum or average of a large number of independent and identical distributed random variables, regardless of their original distribution, tends to follow a normal distribution. Specifically, as the same size increases, the distribution of sample mean becomes increasingly close to a normal distribution with a mean equal to the population mean and a standard deviation equal to the population standard deviation divided by the square root of the sample size. The CLT forms the basis for many statistical techniques and allows for reliable interference and estimation in a wide range of applications. So I hope you guys understood what central limit theorem is. Let's go to the next slide. Now let's look at what are the applications of central limit theorem. The central limit theorem (CLT) has numerous applications in statistics and probability theory. It is widely used in hypothesis testing, confidence interval estimation, and parameter estimation. By invoking the CLT, we can make inferences about population means based on sample means, even when the underlying population distribution is unknown or non-normal. The CLT is essential in quality control, where it allows us to access whether a process is producing items within acceptable limits. It also enables us to model and analyze various phenomena in fields like economics, finance, and social sciences. The CLT's versatility and robustness make it a cornerstone of statistical inferences, providing powerful tools for data analysis and decision making. Now let's take a look at what limiting distribution is. A limiting distribution refers to the distribution that a sequence of random variables converges to as a sample size approaches infinity. It represents the long-term behavior of the variables. The limiting distribution is important because it allows us to make probabilistic statements about the behavior of a sequence without explicitly knowing the exact distribution of each random variable. In many cases, the limiting distribution is well known, such as normal distribution in the central limit theorem. Understanding the limiting distribution helps in making statistical inferences, constructing confidence intervals, and conducting hypothesis tests, providing insights into the behavior of random variables in large samples or asymptotic scenarios. Let's go to the next slide. Now let's look at laws of large numbers. The laws of large numbers are fundamental principles in probability theory. The strong law of large numbers states that as the number of trials or observations increases, the sample average converges almost surely to the population mean. This means that the probability of sample average deviating from the population mean becomes vanishingly small. The weak law of large numbers states that sample average converges in probability to the population mean. It implies that the probability of the sample average being arbitrarily close to the population mean approaches 1 as the sample size increases. These laws form the basis for reliable statistical estimation and provide a theoretical foundation for understanding the behavior of averages in large samples. Now let's take a look at weak and strong laws of large numbers. The weak law of large numbers states that as the number of trials or observations increases, the sample average converges in probability to the population mean. This means that the probability of the sample average deviating from the population means by a large amount decreases as the sample size increases. The strong law of large numbers, on the other hand, states that the sample average converges almost surely to the population mean. This means that with probability 1, the sample average will eventually be arbitrarily close to the population mean as the sample size increases. Both laws establish the convergence behavior of sample averages and provide a foundation for statistical inference and estimation. Now let's go to the next slide. Now let's look at what are stable distributions. Stable distributions are a class of probability distributions that exhibit a certain degree of stability under addition. They possess a unique property where the sum of independent and identical distributed random variables properly normalized follows the same distribution as the original variables. Stable distributions have heavy tails and can model extreme events or outliers more accurately than normal distributions. They are characterized by parameters such as stability index, skewness, and scale, which determine their shape and behavior. Stable distributions find applications in finance, physics, and telecommunications where modeling non-normal and heavy tail phenomena is crucial. Their mathematical properties and stability under convolution make them valuable in statistical analysis and risk assessment. Let's go to the next slide. Now let's look at stable processes and their applications. Stable processes are stochastic processes that exhibit similar stability properties as stable distributions. They are characterized by the property that the sum of independent and identically distributed increments properly normalized follows the same distribution as the original process. Stable processes provide a flexible framework for modeling a wide range of phenomena with heavy tail and long range dependent behavior such as financial asset returns, seismic data, and telecommunications traffic. They allow for accurate modeling of extreme events and capture the persistence and clustering of observations over time. Stable processes have applications in finance for risk management and option pricing, in geophysics for earthquake modeling, and in telecommunications for network traffic analysis, among other fields. Now let's look at what is convergence in probability. Convergence in probability is a concept in probability theory that describes the behavior of a sequence of random variables. It states that as the number of variables in the sequence increases, the probability that these variables deviate from a given value approaches zero. In other words, the variables become increasingly likely to be close to the specified value as the sample size grows. Convergence in probability is denoted as xn gives rise to p of x and is a weaker form of convergence compared to almost pure convergence. It plays a crucial role in statistical interference, allowing us to make statements about the behavior of random variables based on large samples and establishing the consistency of estimators and tests. Now let's look at what are limit theorems for dependent variables. Limit theorems for dependent variables extend the concept of convergence to sequences of random variables that are not necessarily independent or identically distributed. These theorems provide insights into the behavior of dependent variables as the sample size increases. Examples include the Ergodic theorem and the central limit theorem for dependent variables. These theorems establish conditions under which the sample mean or sum of dependent variables converges in the distribution or almost surely to a specific limit. Limit theorems for dependent variables are essential in analyzing time series data, spatial data, and other correlated data types and enabling statistical interference and estimations in situations where independence assumptions do not hold. Empirical distribution function. The empirical distribution function is a non-parametric estimator of the cumulative distribution function based on observed data. It assigns a probability to each data point by counting the proportion of observations that are less than or equal to that value. The EDF provides an approximation of the underlying CDF without assuming a specific parametric distribution. It allows for visualizing the data distribution, comparing different data sets, and performing goodness of fit test. The EDF converges to the true CDF as sample size increases following the Glivenko-Cantelli theorem. It is a versatile tool in exploratory data analysis and forms the foundation for non-parametric statistics. Now let's look at the conclusion of convergence and distribution. In conclusion, convergence and distribution is a fundamental concept in probability theory and statistics. It describes the behavior of sequence of random variables as the sample size increases, leading to a limiting distribution. The CLT theorem is a key result within this framework, stating that the sum or average of a large number of independent and identically distributed random variables tends to follow a normal distribution. Understanding the limiting distribution and its properties is crucial in statistical interferences and data analysis. While convergence in probability and stable distributions provide additional insights, the field continues to evolve with challenges, extensions, and new applications. Further research and advancements in convergence and distributions offer exciting opportunities for future exploration. Thank you, and I hope you understood the topic about convergence and distribution. Nice. Yeah, let's go next time. Bye.